Hi there. Can they hear me? I believe that they can. Okay. Okay. Cool. Well, hello everyone. Happy Saturday. Um, I apologize for the technical difficulties. My ancient Linux computer, I think, has finally kicked the bucket. Um, rest in peace. So this is a PDF. I hope that the formatting is all correct. I'm crossing my fingers. Today, we're going over the chapter 6 of the Mathematics for Machine Learning book, Probability and Distributions. This chapter contained a lot of equations, and it was, well, there was a lot of it. So I won't be doing, say, like too much of a deep dive, but I think that or into individual topics, but we can definitely discuss or elaborate on some of the topics as they come up. So, with that in mind, um, I'm just going to go over the different concepts that they presented in this chapter. So they started off basically by defining a couple of terms, probability distributions being equations that describe the likelihood of random variables, a sample space. They basically gave an example of flipping a coin two times. The sample space would be the set of all the possible outcomes, like, heads, heads, to tails, tails, and everything in between. The event space being the subset of that sample space with a particular outcome in mind, um, such as, at least one head, which would be the first three elements in that sample space, but not the fourth. And then the target space being the set of values that you care about that can result, like the number of heads, zero, one, or two. Now, as you can kind of tell, between the sample space and target space, that's it's not like a one-to-one relationship. So it's not bijective. Um, there's less elements in the target space than there are in the sample space. So the random variable is the mapping for that for where X maps the sample space to the target space. Is the definition. So, in order to describe the likelihood of this random variable or this mapping, if it takes on discrete values, the nomenclature is probability mass function. So basically, they gave this handy little grid, which I will also refer to later because I think it helps with intuition. Basically, this cell Nij, is the probability where x equals x and y equals y. And all of these cells are normalized, so they all add up to one, which is, for PMFs or PDFs. The marginal probability is the probability where one of the random variables or one of the variables equals a particular value. So like the probability that x equals x4. So that's the sum of all the probabilities in this column divided by the total. Same thing with py, like the. Sorry.
Um, Zoom screen sharing was on.
Zoom screen.
That was my fault.
Oh, whoops.
So the people online.
So, oh, okay, there we go.
It's not in your way.
Cool. Do we have the volume turned on for the remote people?
Uh, you'll hear it out of your computer speaker.
Okay, cool. All right. Yeah, so sorry about that. I'm gonna see if I can go back a slide. Oh, whoops. There we go. Yeah, so sorry, this was the previous slide, sample space, event space, target space, and then random variable being a mapping from the sample space to the target space. Um, I hope everyone got that, but there'll also be a copy of these slides available afterwards. So yeah, discrete distribution functions, the probability or the marginal probability is just the probability of with respect to a single random variable. So the probability that x equals x4, which is, the sum of all these cells uh, in x4 divided by the, total number. Same thing with, the probability that y equals y2. Um, and then the conditional probability is, or the probability of y given x, or the probability of x given y is, say, the probability that y equals 2 out of all of the cells where x equals 4. So we don't care about the rest of the um, grid, just where x equals 4, and then the probability of this. Conversely, same thing where the probability that x equals x4 out of all of the probabilities where y equals y2. So we only care about this row and the probability that x equals x4 out of this row. So um, yeah, moving on, basically, try and move on. The what we talked about was for a discrete random variable. For a continuous random variable, you can't actually, have a particular value because it doesn't make sense. It's like, what's the probability of throwing a dart at a dartboard and hitting a particular point? If that point is infinitesimally small, it's basically zero, or it's undefined. It doesn't really matter. So for probability density functions, which is PDF as opposed to PMF, we look at intervals. So what's the probability that this value will fall in this range? And then we take the integral of that. Cumulative distribution function, or a CDF, is basically the likelihood that there was a formatting issue. Oh boy. um, that a random variable is less than or equal to a particular value. So the examples that they gave were like, if you have x to xd, or a particular set of, in x, then you have to integrate for each of those dimensions from negative infinity to, whatever the value is, and that gives you the CDF, or cumulative distribution function. So, and then the uniform distribution is basically, they throw this out, but they never really define it. It's very simple. It's just a flat line. All results are equally probable. So,
Hey, Liam,
yeah.
before you move on, just a quick note. It's not super important, but the cumulative distribution function, the CDF, does help unify discrete and continuous probability. So if you look on the left for discrete, you have probability like dice. There'd be 6 points and each has like a 1/6 probability. Whereas for something continuous, you'd have this smooth function. Okay. So you can't really talk about the two diagrams that Liam has, the PMF and the PDF, the same. However, they both will have a CDF. Okay, the CDF for the continuous distribution will look continuous, and it'll generally it's some sort of like S curve, like, right, because it goes sort of from 0 up to 100%. Okay, the if it's a discrete distribution, it'll be discontinuous. It'll be a step function. So every place where there's probability, like the 3 dots on there, CDF is going to jump up all of a sudden, and it'll be discontinuous. So it'll look like a sort of a stair step thing. But it does exist, and it has sort of all the same properties as the continuous one. So if you look at other statistical texts, my understanding is that the CDF is kind of the way that you can talk about all distributions, both discrete and continuous, kind of similarly.
That's a good distinction to make. In fact, I don't think yeah, that's a good distinction. I don't think they make that incredibly clear in the text, but they definitely should, because that's
Yeah,
That's
and there's other gory details, and they say explicitly in the text that they're ignoring a bunch of details just to make the basic concepts clearer and not get bogged down in some of the technicalities. But otherwise, you might ask, why do we even need to introduce the CDF? We could just use the PMFs and the PDFs. And there is there is a whatever complete one-to-one relationship between a PDF and the CDF. So if you know the CDF, then you basically know the PDF. Again, there's technicalities, but like, um, uh, yeah. So excluding like zero measure discontinuities and things like that, you can derive one from the other. Yeah.
Also, I have a question. So CDF is like the thing that unifies discrete and continuous. Are you saying that, just, I guess for clarification, are you saying that in order to understand the CDF, you have to understand the discrete continuous? And once you understand those, this is easier to understand it like that. But then once you understand those, you're just going to use it in the context of the CDF.
So basically, this is my lay way of saying it. It's kind of annoying for mathematicians to have to do every proof, everything twice, once for continuous, once for discrete.
Right.
So if you can find a way to unify them, then you can do a proof once, and then the proof is done for both cases. Otherwise, they'd have to just sort of do everything twice.
Okay.
And so it's not really that there's anything big and important about it. It's just extremely inconvenient
Okay.
if you don't unify them.
Okay. Got it.
Yeah.
And is it more difficult to understand it without knowing how the discrete and continuous work? If that makes any sense, because like sometimes with math they'll do something like that to make things more convenient, but then like to teach it in the context of the convenient method may be more difficult to understand. But it's the way people do it. If that makes any sense.
Yeah, I'm not sure. I mean, like I said earlier in the room, probability and statistics is probably my weakest math subject.
Okay.
But the general gist is that if you're just worried about practical applications, none of this stuff is really a problem.
Okay.
But there are just technicalities, and there are so like when you sort of combine the probability of rolling a one and rolling a two, you can just say like plus, right? But in a continuous distribution, what you're really doing is you're adding infinitely many zero probability events. And so you need some math to like formalize that, because otherwise that's not well defined.
Right.
But if you think about something and you're like, I have a uniform distribution between 0 and 6, whatever, like 1/6 of that has probability 1/6, right? It's pretty intuitive. There's just some very funky math that you need in order to formally do it right.
Okay.
Yeah, and I've personally used the CDF. It had like an application in finance, just because you're dealing with like fixed thresholds, and you want to like test like across multiple, say like instruments, etc. But that was very brief. But anyways, are there any more questions regarding these things so far? This terminology?
What's the most package?
Integrals? Yeah. Well, the for continuous variables they do. So as Ted pointed out, there can be a cumulative distribution function for a discrete variable. It's just like a stepwise or non-continuous function. Stepwise, technically, I guess, right? But if you have a continuous variable and you want to calculate the cumulative distribution, it's basically the same thing as calculating the probability district or the PDF. You just, instead of taking an integral between two thresholds, you just take it, negative infinity to a particular threshold. Did that kind of answer? Of course. Anyone else? Okay. Gonna move on then. Okay, so I don't know if this gets cut off here. Again, formatting issue. Wonderful. Okay, so just a couple of quick probability rules, right? So I brought this grid back up again because I think it's helpful to sort of have a visualization. Um, Basically, the probability of x, if y is discrete, is the sum of all of the probabilities in that state y given. Anyways, I'm gonna let me show you what that looks like. So basically, the prob if you want to take the probability that x is x4, right? Then you just want to sum up all the probabilities of x and y for each for each state y in the total y. So basically, what it's saying is you just sum up each of these cells. So, like to get out of the total. So, and we're assuming again that this all normalizes to one. So you'll be left with, 0 point something or other, hopefully. And then if y is continuous, you basically just do the same thing, except you use an integral instead of a sum. And you could do that with multiple dimensions as well. You just have to, that's basically how you do it. The product rule, basically the probability of x and y is equal to the probability of y given x times the probability of x. So if you were to say, give me if you want to say, get like one of these cells here, you could get the probability of y given x. So we only care about this particular column. And so this inner cell out of all of these in this column times the probability of it being x4 out of all the x values, right? So, and that kind of makes sense. It all, comes up to one. So that's the product rule. And then Bayes' rule, I've attempted to do this while practicing. It's actually kind of difficult to get a geometric, intuition for this without like putting this in equations. But I'd recommend if you want a geometric interpretation, check out Veritasium has done a video on this. It's very useful. I will attempt to kind of explain it in this way. So if you want to get the probability that x is x4 given y equals y2, then you need to get the probability that y is y2 out of all of these x values for x4 times the probability that x is x4 divided by py. And actually, now that I mention it, that there's actually a relatively easy way to describe this. So that will give you py given x times px will give you the probability of this particular cell. But we want the probability of x given this y value. So that's why you divide it by the probability of y2. So yeah, and there's a lot cleaner geometric ways to interpret that. But as I said, check out Veritasium. We did a good video on that. So any questions regarding that? Quick questions? The what? What's the prosecutor fallacy?
You want to go that?
I
So everybody can see it. Not that I don't know what's happening. Everybody can see it on the screen.
You think it's okay if I Google this? Actually, could you just maybe like describe it really quick?
Sure. So, how does the additional evidence change the jury's perceptions about whether a suspect is guilty or not? I was assuming that we can use Bayes' theorem to explain that given the suspect is like what kind of evidence we know about it, how likely jury votes this person is guilty or not.
Absolutely. In fact, it depends on what your prior is. So like most of the time that I've seen this, you have like a prior which is like a guess of what you think P of X is going to be, or a guess, or you have data, etc. And then you are concerned with this likelihood, like actually, how do I make this full screen again? Tab?
That little menu in the lower right, I found, I think that one, yeah. I found full screen mode.
Nice. Okay, all right. So and what you care about, so you have like, and maybe you have some evidence too, but you care about this, X given a particular value for Y. Um, Maybe like that an event is occurring, on a particular page, like an error is occurring on a particular page. Um, and like given a set of evidence, like basically like uh, what is it? Boundaries for your environment, right? What's the probability that a particular thing happens or is a particular value? In this case, maybe a guilty verdict or a not guilty verdict, which could be represented by like binomial or Bernoulli or actually even a beta conjugate prior, which we will be getting into maybe, but which we will be getting into in a couple slides. But um, it should actually be a little bit uh, more clear. But the prior in this case might be like you know, uh, likelihoods in the past for precedent, something like that. Um, but yeah.
So before you move on, I think that the book might lightly mention this at some point, but it's probably useful to just share that by convention, when we do machine learning problems, we often use Y and X in particular ways. So Y's are your labels for supervised learning, okay? And X's are your datas, but the data without the labels. So when you combine the two together, then you actually have a labeled example. So Bayes' rule is written this way. It could have been written with the X's and Y's reversed, but it's written this way because of the convention that we have with um, with with data and labels. Okay. Um, so uh, so basically, it's useful to it took me a long time, honestly. It's useful to get familiar with these particular pieces and understanding how they work. Okay, so like a likelihood label given data, right? So let's say your data is a photo of a part coming off an assembly line, and your label is this defective or is this a good part? Okay, so then the likelihood is the likelihood that this part is defective. I find that to be perhaps the most intuitive term. Okay. Now your prior is basically just is it's just X. So it's just the distribution of images of parts. Okay. And then the evidence, the PY, is what's the rate of defects overall in your data. Okay. And so then the posterior is the thing where basically is the distribution of images given the labels. So when you see something, a term like maximum likelihood, they're actually talking about that particular likelihood in this formula.
Okay. This is how the likelihood to the probabilities of certain features are, this is how you come up with that number, that probability value.
I'm going to hold off answering that
Okay.
question. I think like chapter 10 is going to like really get into that.
Okay.
But just to share that like although we may not explicitly be using Bayes' rule to calculate the numbers of the probabilities, this relationship is a relationship that underlies, and I think it will get clearer in part two when we kind of go through specific things like linear regression. But I just wanted to mention, since it's coming up now, that like there's a way you can explicitly use Bayes' rule to say, if I know, like I think one of the exercises at the end of the chapter, it's a little bit like on the right where Liam has a little grid and you have certain probabilities and they say like, oh, this bag has 2/3 mangoes and this bag has 1/2 mangoes and blah blah blah. Figure out. Yes, you can use Bayes' rule to explicitly calculate things, but it's also sort of the underlying principle for more complex situations.
All right. Yeah, so moving on, probability rules. The next thing that they talk about is this concept of expected value, which is, of course, used a lot in, machine learning texts, papers, etc. Naively, I sometimes think like as I'm reading expected value, I do think like, oh, this is a glorified mean. I know that's wrong. It's more like mean is a variety of expected value. But basically, a mean would be, or the expected value is defined as the sum of all of the elements of X multiplied by the probability that X is a particular value or X is that value. So if you say like, have a uniform distribution and you have like a set of 10 numbers discretely, then the mean is going to be 5 because they all have the same probability, 1 out of 10, and then you multiply each by that number. So you get 5. And then with a continuous value, again, it's the same thing, but you take an integral. But you can also extend it to stuff like functions, which basically, expected value of a particular function is the sum of all like either inputs to that function by the probability or the integral there. So it just transfers over. If we're talking about X as a vector, then the mean is basically or the expected value of X as a vector is just the expected value of each of the dimensions of X. And this equation that they gave in the book on the right basically just goes over a couple of properties of expected value. Basically, the setup here is that f of x is equal to a times g of x plus b of h of x. And basically, what this just shows is that these scalar values a and b are distributive. They can be taken out as well as you can apply. It's the same thing as applying the expected value to g and the expected value to h, and then multiplying them by each of those corresponding scalars. So that does anyone have any questions about that before I go on?
By the way, they reference this later in the chapter several times.
Yeah.
But they do it. The formal terminology they use is that expectation is a linear operator. Okay, so if you have the expected value of two things added together, you can just take the expected value separately and add them together. If you have the expected value of a scalar, like 2 multiplied by something, you can take the 2 right out of it, and you can just say 2 times the expected value of the basic thing. So that's very convenient when you're working with expected values, because it means that generally speaking, unless you have something that's like a function of x when you're doing the expectation over x, you can just rip everything out of the expected value equation. And when you're reading an ML paper and it's a very complex multidimensional thing, if there's something that only depends on W or Z or whatever, because it doesn't depend on X, if you're taking the expectation over X, you can also rip those things right outside of the expected value and just stick them on the outside, whether it's a multiply or an addition.
Absolutely.
So that happens a lot when you see equations getting kind of like rejiggered. It's because they can just yank all sorts of things out of an expected value.
And you can kind of get a sense of why. I'm going to use like this equation right here. Like if this was g of x plus h of x, or expected value, yeah, then that would mean that in parentheses, this term g of x would become in parentheses g of x plus h of x. So if you take the sum of all of those times, the probability, then it's the same thing as if you were to, you know, uh, uh, distribute that out and then take the sum of each of those. I'm not doing the best job of describing that, but it does kind of make intuitive sense why. Just like if you had like a scalar value here, and you're summing all of these up by like, and they all have a two in front of them, well, yeah, you can just take that two out and multiply it by all the sum because each of those values are also multiplied by two. So did anyone have a question here?
I'll add one more comment again. So you'll see what I said before, you'll see that a lot in ML papers. The other thing you'll see is people wanting to use that trick, but what they have isn't quite in that form yet. So what they'll do is they'll multiply and divide by the probability of X. Okay, so if you have some expression and you multiply it by P of X, you also divide by P of X, then you're just, multiplying by one. Okay, but they group it so that it's the blah thing times P of X, and then separately the whole thing divided by P of X. Okay, so then what happens is when you have something, a sum or an integral times P of X, you've now turned it into an expectation. And now you can use all the rules of expected values to move things around in and out of the expectation. So that's a trick that you'll often see is they multiply by P of X over P of X in order to do the earlier trick.
When should I care about the linear structure you just mentioned about? If EX plus Y equals to X.
I would say that you're probably not likely to use that ever day to day. I mostly only use it when I'm reading papers, understanding how people turned equation 1 into equation 4 or something like that, and that's,
Yeah,
like I said,
it's in a lot of papers, honestly. Like, I think like the last time I saw it, it was like a paper with Monte Carlo stuff. Um, yeah, it's in a lot of papers because people want to sort of understand, like, well, what their expectations are for a particular model or for a particular process. And that can be more complicated than the mean. In fact, in the chapter, they had a nice little graphic which I didn't display here, but comparing like the median and the mode and the central value. There's a lot of different ways to, you know, determine this sort of like central point, right? Um, but expected value kind of gives you a way to determine that, but with more complex operators, like most models just being like, equations, you might want to know what the expected value is of, some of those processes. So, okay. So now that we know about expected value, we can use that to sort of get a more formal definition for covariance and variance, which is, I've always heard this kind of described like algebraically, not necessarily in these terms. But in terms of like expected value, if you want to say get the covariance between two, random variables X and Y, then you can get the expected value of the deviation from the mean of that of X times the deviation from the mean of Y, and then get the expected value of that. Basically, and you can even use those rules that we just went over to basically turn it into the expected value of X times Y minus the expected value of X times the expected value of Y, which again just kind of gives a numeric value of how these two, the deviation from the mean and these two random variables relate to each other. And I'm really like yeah, it's it's kind of it's challenging to think of like a geometric intuition for this. But just to say that it is like, measuring the difference from each of the means of these two random variables. Um, Actually, Ted, do you have maybe like a more intuitive way to describe this?
So for me, with my weaker probability background, I'm more familiar with I have a better intuition about correlation than covariance. So I've seen correlation a lot. So a correlation of 1.0 exactly means that they have a perfect linear relationship. So if you plot a scatter plot, you'll see a line sloping up to the right. It doesn't have to be slope one. It could be slope two. It could be slope one half. But basically, if you double one thing, the other thing will double. Okay. If it's -1, then it's also perfectly linear, but the slope is negative, so it's up to the left. So if you double one, then the other one will be -2 times itself. And if it's 0, then that basically, if you just think about unimodal things, then it basically means that the two of them are orthogonal, they're perpendicular to each other. And no amount of change in one variable tells you anything about the change in the other. So X could change a lot, and that doesn't tell you whether Y changes a little or a lot. They're just completely independent of each other. Okay. And so if you plot a scatter plot for just unimodal distributions, if it's correlation 0, then it might just look like a circle, like what they call just like a shotgun scatter, where there's just no particular pattern. And the more oblong it is, the closer the correlation will be to 1 or -1. And then if it's exactly 1, then it's no longer even an oval, it's just a perfect line, with width 0, an oval with 0, right? So that's what the correlation tells you. And then the covariance is really the same thing, it's just not normalized. So the covariance is not limited between 1 and -1. It can be, just sort of any number.
Absolutely. In fact, yeah, like the variance, it really is normalized by the variance of each of those random variables. So it's always between -1 and 1. And I think a lot of us have worked with, correlation matrices, and it's usually more helpful to put it in terms of -1 and 1, with 1 being, a perfect positive relationship, varying 1 equals varying other, and -1 being, an inverse relationship, like increasing 1 decreases the other. It just like this part that I'm trying to come up with like an intuition for is that the covariance equals like the expected value of Y times X minus the mean of X times the mean of Y. But it kind of makes sense. I mean, again, we're measuring the difference between X and its mean, and we're measuring the difference between Y and its mean. We're putting that as we're basically creating a vector of that. And then we're taking the expected value of that. And so, yeah.
Yeah, I mean, I can give a slight intuition. So imagine that you have two variables that have very high correlation. They move together positively. Okay, so the correlation is close to +1. Then when they have a center of mass, that's their mean. Okay, then when it's far from the center of the mass, they're both going to be far away. So when you multiply them together, you're going to get a really big number. Okay. And then you're just subtracting, on the right, you're subtracting the mean. If they were not varying together, then you'd get a lot more random occurrences of X being big, but Y being small. And so then overall, your products on the left half of that equation are just not going to pile up as fast as, the easiest way to get a big number is when you multiply the really biggest X's with the really biggest Y's. That would be my. Now, whether or not that proves that equation, no, but just as an intuition, why the more they vary together, the more that becomes a bigger number in that equation. I would say that's the best I could do. Yeah. The other thing is the book does mention, and you might have this on a later slide, but this is a linear relationship only. So this is not predictive power. So you could have y equals, I don't know, x cubed, and perfect 100% predictive power that if x is 3, y is 27. And the correlation for this is not going to be 1.0 because they're not linearly related. So just know that there's a difference between whether or not there's mutual information, whether there's predictability, and whether or not there's a linear covariance or correlation property.
And one more thing that I would mention actually is like if this value would be negative, say if if x increased and y decreased, then this value would end up being negative because y would, or one of these would become, say negative while the other became positive because they would increase and decrease in different directions. The mean would become negative. So, and then variance is just basically, square deviation from its mean, essentially, or the variance is just the covariance of x with itself. And so you could rewrite this as covariance of x of y over the square root of covariance with itself of x, covariance of itself with y, square root, because you're basically squaring this in covariance if you get the covariance of it with itself. So you want to take the square root. So it's a more accurate representation of the, deviation. So.
Okay. Just clarification. We've been working through this, so I'm gonna make sure. So for covariance, the way I'm understanding when I look at that equation, it's saying the average value or the average outcome of x and y happening minus the average of x happening times the average of y happening.
We wouldn't say x happening because we're assuming right now that x is a either like one of many. We're not assuming that x or y is a binary value or a zero value. We're more like thinking of it like imagine like x is a vector, right? A series of numbers. Then we're taking, a vector x and we're subtracting it from, its mean, essentially, the mean value, which we could represent as a vector, but you could also just represent as a scalar. It's the same thing. And so we're basically taking these numbers that could mean anything and we're representing them in terms of, its mean value, deviation from the mean value. And then we're just basically comparing like how this varies with x and how this varies with y.
Okay.
Yeah.
So
And
like I'm sorry.
and as in terms of say machine learning, where x is like the observations, and y is like the labels, then well, actually, that's not really when you use that. Actually, forget I said that because that's not how you would use covariance. You use it for features, but yeah. So
Okay, so there's like something that we want to know will happen. And then there's like two variables, x and y, that we're measuring like how like correlated they are to that one thing we want to know. So that's what covariance is like.
no, actually, that was I misspoke. We're usually use like correlation and covariance to determine how closely different features are related before labeling. So like,
Okay,
yeah,
okay.
so like, does the day of the week, actually that's a bad example. Does the number of users accessing a, given page correlate with the number of anomalies on that page? Something like that.
Gotcha.
And if so, how much? So
So how each feature is like
correlated to each other.
correlated, like how much they influence each other potentially. or like associated with each other?
Yes, yeah.
Oh.
And then like if you have a lot of features that have a high correlation, you could probably take out a couple, or you could, you know, yeah. Okay, so anyways, some useful properties of variance and covariance is that, given an affine transformation, which we covered in chapter 2, basically it's single, like equation of a line, single layer in the neural network or whatever it is, X input features times this transformation matrix A plus some value B, affine transformation, we can model the expected value of Y just using that transformation matrix and the mean of X plus B. And the way that we can do that is through those steps, we can factor out this transformation matrix A, and then use EXX to kind of mean the mean, and then just model it in this fashion. With the variance, what you can do is you can actually, reduce it to be A times this covariance matrix times A transpose. So all you actually need is the covariance of X with itself, What this also means is that this covariance matrix is a similar matrix to the variance, which might have some interesting properties that I don't really know how one would use yet. But and with the covariance, you can actually reduce it down to be the covariance of X times A transposed, which is kind of interesting that you can then just apply A, or the transformation, on the front end of this and then turn the covariance into the variance, which kind of intuitively makes sense because variance here, or yeah, you might have to think about that one a little bit, but I just think that's kind of an interesting couple of things that they put forward in the book. So yeah. Anyways, and another thing that they brought up in the book that I thought was very interesting is this idea of covariance of X and Y as an inner product. And then this idea that, like, okay, so we have this covariance matrix, and that's a matrix just like any other matrix, which can describe vectors that exist in space. And so we can come up with, like, geometric properties of variance, of distributions, kind of spatially. So in this figure, right, they gave the example of, two, we say that like two random variables are statistically independent if the variance of X plus Y equals the variance of X plus the variance of Y, which means that they don't really like, change each other at all. So that means that the inner product, or I'm sorry, yeah, the inner product equals 0, and they're orthogonal in space. And then so this is, a right triangle. The variance of X plus Y, square root of variance of X plus square root of variance plus Y, is equal to square root of variance X plus Y. So that's kind of a property that you can derive this equation just by representing the variance as vectors in this vector space. And then you can take the correlation is actually the cosine of theta here. So, and this field is called information geometry. I don't know the first thing about information geometry, I got to be honest. So I wanted to kind of open it up and ask if anyone in this group has worked with information geometry at all, or has, used it, because I think it's fascinating and I haven't really dived into it. So I'm also kind of curious if I can hear the people on. But yeah, has anyone worked with information geometry at all?
I haven't worked with information geometry, but I have been reading the books of linear algebra, and this is blowing my mind right now because of whatever I'm reading. Because I actually have a question. So, like, when you're programming these systems, because I'm assuming that the vectors that you're using to create your space of possibilities, possible outcomes and stuff, like they're not naturally orthogonal because we're trying to represent real world stuff. So how do you guys go about like making these vectors orthogonal? Is it just purely mathematical, or do you got to get like some physical intuition about
Okay,
it?
so if you have, this is an extreme example because this actually probably would not be the case ever. Um, but assuming that you have something that's like completely independent, um, like the color of someone's shirt in RGB continuous values, like compared to I don't know, their scores on like the SATs or something. Um, any correlation between those two things is absolutely like chance. But so just so imagine that those two things they just don't, there's no correlation there. Um, so the variance of x has nothing to do with the variance of y. So taking the variance of x plus y is just equal to putting those two variances together. It's just like, you know, you're not going to they're not going to affect each other at all. So if you remember like say like the Pythagorean theorem, right? Um if you have like if if you have like the covariance of x and y, and you treat x and the variance of x and the variance of y as vectors, which you can do, right? Um, and vectors describe lines in space. They can also define lines in space. So if you had like the square root of variance x and the square root of variance y, which are vectors, and you can represent them in space just like you could any other vector, then you can actually derive this property v of x plus y equals v x plus vy from the hypotenuse, right? So this hypotenuse is the square root of variance of x plus y, and it is equal to square root of variance of x plus the square root of variance of y. So you can actually derive that um, from its geometric representation. And in chapter two, linear algebra, we went through like a whole bunch of different, properties of matrices and vectors in space. And the idea is just like with information geometry, which is a term I just learned about, like just by reading this. You can basically apply those geometric rules to these quantifications of stuff like I would imagine like distributions. I don't know if it's like only distributions, but definitely, you can apply it to, these qualities of distributions as well.
Right. Um, I don't know if it's too complicated for us to get into right now, but I guess I was asking more about like the coding aspect of it because I understand the geometric portion. It's like because I see you have the magnitude. I'm assuming that's magnitude of the variance of y, magnitude variance of x, right? And you're creating this system where you're trying to measure like the correlation between these two vectors that are orthogonal, so you can apply and they're linear, so like you can apply all the rules to it. It's like when you code it, you in order for like your system to work properly, is it like do you have to explicitly is it like common engineering practice when you're doing ML stuff? Like, are you using some sort of library or somebody figured out how to turn these things into like vectors that can create the space, or do you have to like define these vectors?
Well, I
Like,
mean,
So for the purpose of time, I recommend we take this offline and we can do this as a discussion afterward.
okay, that's fine.
Yeah.
I didn't know
Um,
about it.
all right, so yeah, we go. All right. So one of we've basically discuss like properties of, you know, X, but the actual distribution itself, we like to fit them into general sort of like, hey, this looks like this or this describes this, you know. In this case, a Gaussian distribution is, you know, what we want most data to be. It's much easier to learn a Gaussian distribution than other distributions. And the real utility of this is that you can represent, you know, this sort of normal distribution with a couple of values. That being the distribution's mean, as well as its standard deviation. So this basically a little bit of intuition. This is the equation for it. As you can see, it's the probability of X given mean with the standard deviation and the standard deviation as well. Basically, this term right here just is normal as a normalizing term. And this X is like e to the this. How I like to see this is like as X starts at 0, right? It the it's the difference between that and the mean is high. And so, but then as it like becomes 0, then you get 0 over 2 times the, you know, standard deviation. And so e to the 0 is 1. And so you get this maximal sort of value. You would get 1, which would be the highest value. However, this brings it down to being normalized based on like, you know, how wide it is, essentially. And 2 pi being some identity for a circle that I keep forgetting. So basically, you know, it's we in the book they denote this as n. N takes 2 values, the mean and the standard deviation. For a multivariate density, you use this covariance matrix instead of the standard deviation, essentially, and then you do something, you know, say a little bit fancier here. Well, you just, you know, you treat it like matrices instead of like values. A couple, some properties, and there's more properties on the next page, is that both the marginals and the conditionals of Gaussians are Gaussian. So you can imagine this, if you were to take like a slice of this from any direction, then it would still be a Gaussian. It would just be dispersed kind of differently. And if you were to just take that slice and then rescale it, then it would be like, it would also be a Gaussian curve from any slice of this. So yeah, and that's for marginals and conditions. So a couple of other properties, right, is that if you multiply them together, then you can put them in terms of this C value, which is just a Gaussian distribution of A given B, and then A plus B. And they give this big identity for this, honestly, if I remember correctly, and it's just a lot to put on here. What's more intuitive is the sums of Gaussians. So if basically if you have like P of X plus Y, then you can get the Gaussian distribution and just add the means together, and then add the what do you call it? The covariance, covariance matrices together to get a Gaussian of both of these. Scaling doesn't work the exact same way because if you remember, there's this idea of the covariance squaring the initial value. So you actually have to square the scalar in order when we're talking about the covariance matrix. So scale the mean, but scale the covariance by it squared. So yeah.
Hey, Liam, I don't know how important this is, but just if you go back to the previous slide, so the top diagram on the right is a 2-dimensional Gaussian, okay? And I think a lot of papers will talk about the covariance matrix of a particular variable. So in this case, if you have a Gaussian distribution, two-dimensional Gaussian, so x1 and x2, if that covariance matrix is diagonal, okay, then basically what that means is that this Gaussian distribution, as we see it, would be either oriented along the x-axis or oriented along the y-axis. Okay, so if your diagonal matrix has the same values in both positions, then what you'll see is something that I don't know what to call it, but like sort of like a circular bell-shaped Gaussian. Okay, so imagine they both have mean 0, and if they both have variances 2, then you're going to get something that's symmetric in all directions, and it's going to look like an actual physical bell. Okay, if you have different values, then it can be longer. So if it's like 2 in the upper left, and sorry, I wanted to use my words, but 10 in the lower right. Okay, so then what you're going to have is a higher variance, and so now it's going to be stretched. So it's going to vertically be this tall, skinny bell shape instead of a nice circular bell shape. So then you might ask, so when do you have a Gaussian distribution that's not on the axes, that's on the diagonal? So that's when you no longer have a diagonal covariance matrix. So when you have non-zero entries off diagonal. Many times, just because the math gets so much simpler, you'll see where somebody says, we're going to model this as a Gaussian distribution, and then to make our lives easier, we're going to further assume that it has a diagonal covariance matrix, that basically each of the subcomponents, x1, x2, that they're all independent of each other. And what that would look like physically in 2Ds, again, is it's either vertical or horizontal. When they have a relationship with each other, now again, you have mutual information. You know that if it were like a 45-degree diagonal, then you know that, oh, when x1 is bigger, x2 is likely also to be bigger. And so that's that covariance information that's contained off diagonal. And that's super important, but that's a very common thing that you will see is, let's use a diagonal covariance matrix assumption for blah-blah problem to make our life.
When do you know that a lot of methods depend on this Gaussian function, Gaussian distribution? When do you know that you shouldn't apply those?
So not going to get into like central limit theorem, but basically, if you have a unimodal distribution, you can probably get away with something along the lines of Gaussian. So usually what happens is people will start with Gaussian and apply transformations to it so that what you're modeling doesn't have to actually be Gaussian. And the trick is what kinds of transformations you want. The chapter briefly mentions normalizing flows. So in normalizing flows, which were used to for image generation before diffusion took over, what they want are invertible, reversible transformations. And most reversible transformations are not that interesting. So then it's like, how do I actually have, like Liam was saying, you double the Gaussian, it still looks like a Gaussian. That's not an interesting, I need a much more interesting transformation. And most of those, you don't have quick, easy calculations of the inverse. So ultimately what people came up with is, oh, here's a set of transformations that are actually very easy to reverse one-to-one, but they also are interesting. They're non-trivial. They're not simple linear transformations. So that's what often happens is you'll see that somewhere in this map they have a Gaussian distribution, but that's not because pictures of dogs and cats are not Gaussian, right? So they have to find some way to say that there's a transformation or a neural network that learns some transformation, something that lets you actually go from A to B, because once you get outside of the simple world, things, you might say that again, central limit theorem, there may be things like people's heights tend to be kind of Gaussian, you know, but you're not going to have that convenient thing for, you know, like I said, cats and dogs. Does that answer your question?
Sort of giving you the direction.
Yeah.
Quick follow-up for clarification. So, are you saying that we have to somehow take our set of values and make them a Gaussian distribution? As opposed to like be able to like, oh, I know these, there's like particular instances where like, oh, I know this is going to be Gaussian. Or do you have to be like, no, I'm going to make this Gaussian?
Yeah, so for example, the simple intuition for diffusion models that do image generation is if you add Gaussian noise and then you also scale it so that the values don't explode, they stay within your original, you know, range. If you keep on adding noise, eventually the noise will completely overwhelm the original signal and you'll be left with nothing but Gaussian noise. Now, it wasn't intuitive to me when I started learning ML, but if you actually took RGB values and you randomly assign them Gaussian, it actually looks like that snow that you see in an image. Like 1D Gaussians don't look like that, but high dimensional Gaussians actually look like that. And so when you see something, an image that's just completely noise, it's that snowy looking thing. Okay. So this is really great because I know that I can turn any image into a Gaussian just by repeatedly adding noise. The problem was for the longest time, nobody could figure out how to reverse that process. And so it actually took some people doing some experiments and having very powerful computers to say, wow, I can actually teach a neural network how to reverse that process. And it turns out that that still doesn't work very well. You run into problems where it won't learn. So then there were additional tricks that were needed in order to get it to actually work. But then ultimately, yes. So that's a very straightforward case where we know what to do with Gaussians, and we know things like I keep adding more noise. The sum of two Gaussians Lian has right on there is or the next slide that I asked you to move back from. We know that that's Gaussian also. So there's all these nice properties, but at the end of the day, it's not because, you know, you wanted an image generator to be able to do, you know, an astronaut riding a horse that's not a Gaussian distribution. You need to do a big transformation. And the question is, can you learn a really good one?
Yeah, and honestly, like most good features, well, not most, a lot of good features are Gaussian in nature. Like if you were to say it, and you could plot this by like creating like a histogram or something, you know, bin them by particular values. It's probably going to look something like this. And you can measure stuff like kurtosis on top of that, right skew, left skew, stuff like that. But again, then you can apply a linear transformation or something and make it a Gaussian. And I mean, it kind of makes sense. Like, you know, if you have this like most common value, you know, you can expand it and you can contract it. And it's like, you know, using this E, which is very often found in nature. And if you were to say plot like say the histograms of a particular feature, and you see like two humps or like, you know, like the weird kind of pattern, that's usually a good indication that you need to like combine some features or there's processes working on that feature that you need to go and explore and find what they actually are. Because you know, there's typically like if you have something that has like more than one hump, essentially, that usually means that there's like, you know, something else at work here. Three humps, maybe like, you know, an oscillation of some kind. You know, and you want to kind of do a little bit more digging because putting it in this Gaussian format makes it much easier to work with. And condense, which I'm going to get to in a second with exponentials. But yeah, so in any case, sums of Gaussians, products of Gaussians, etc. Any further comments on Gaussians? Okay. So, this thing is in the top. Okay.
Just
Okay. So, we talked about Gaussian distributions. It also mentions three other distributions. There are more. In fact, there's a whole table of these in the back, I think. It's table 6.2 or something. Talks about conjugates, but just, really briefly, a Bernoulli distribution is basically gives the probability of X if X is like a binary value of 0 or 1. This equation right here, I actually forget what it actually calls these two terms. I really do. But essentially, like if oo here is like 0.4 or something, then this term right here basically gives you represents like the probability of the positive thing happening, and then one minus u, the one minus x, is the probability of this of a negative thing happening. So like 1 minus 0.4 is 0.6. So this represents the alternative or the negative thing happening. So probability that x is one in like a very simple sort of way. The binomial distribution is, the probability of observing like m occurrences in a set of n samples of x equals 1. And I've actually had to use this in the past when it comes to customer journeys and stuff. I will say that this is actually computationally intensive to calculate. It's n choose m, where there are factorials involved. But and So it looks very similar, except you're figuring out the probability of m samples given n samples with this value, which is mu. Um, Now, a beta distribution will give you more like an uncertainty of a continuous random variable, or like this alpha parameter is the number of successes, beta is the number of failures. I'll give you an answer like there's a 95% chance the success rate is between 3% and 7%. This also allows you to update this gamma parameter based on like, repeated observations. So it's useful if you don't like already know, the values, and you can like update this over time with time steps. But beta distribution, more common with uncertainty. And honestly, I can see it being used more because I haven't like found a need for a beta distribution yet. And I think it makes more sense actually with this, which is this idea of conjugacy. So I brought back this equation, right, for Bayes' theorem, just so you have a visual sort of idea of this. So a lot of the times we get stuck with this prior and we don't actually know what it is, right? Like say you're doing A/B testing, you don't really know how to calculate like the prior of like, oh, this is probably going to happen like, this amount of times. What you can do is basically if the posterior distribution is going to be of the same family as, I'm sorry, if the likelihood function uh, posterior, if the posterior, yeah, it's was actually that's yeah, as if the posterior is the same family as the prior, then you can basically represent this as a conjugate or the posterior as a multiplication of a probability and its conjugate. Um, One of the examples that it gives here is like, so this is the binomial distribution, right? So if you want to say like get the number of heads where mu is the probability of heads, you kind of need to know what mu is supposed to be. What's like the median value. Well, imagine it's, I don't know, kind of a weird coin where it's not like, intuitive just by looking at it, that's going to be 50%, or some other thing, you might want to calculate that over time. You might want to use a gamma distribution to do that. So in order to find this posterior, you can actually just multiply that you can find the probability of x given n, where u is this input parameter, But for estimating this prior, you can use the beta distribution, which is probability of this mu mean value given A and B. And if I go back to the beta distribution, A and B is like the number of successes and the number of failures that you can update over time. This gamma function, you can take the last time step and you can, kind of, aggregate it. So, if you were to say like, if you were A/B testing and, you had a mythical 30% conversion rate, right? And 50 successes and 150 total observations, then you could update this over time to give you a more updated, posterior distribution or a conversion percent chance or whatever you're, looking at. And you can get this like probability of oo given x equals h and all these input things, right? Um, and you can do the same thing of this with the Bernoulli distribution as well. So if you have like Bernoulli trials, you can also add this beta distribution where a or alpha and beta are number of successes, number of failures. You know, so that makes it a lot easier to estimate the prior over time. And I assume there's a lot of other ways that you could do this. There's a lot, there in the back, there is a conjugacy table. So before I go on, are there any questions about conjugacy?
For me, Liam, like there's a lot of the mathematical properties, but I feel like I don't know if I have this right, but the simple explanation of conjugacy is just like if you look at the base formula on the right and you have the likelihood and the prior, we're going to ignore the evidence for now. You can multiply any two distributions together and you'll get a distribution. Okay. If you want to have a closed form formula for the likelihood and for the prior and wind up with a very quickly derivable closed form formula for the product of those two, which is your posterior, then if you use these exponential family distributions that have known relationships, then you're like, yeah, if I pick this one or that one, then the product is going to have a very simple closed form, and I can just look it up in a book and I can just know. So that if the first distribution depends on these variables and the second one prior depends on those variables, in 5 seconds, I can look up what the exact formula is for the posterior that's the product of those two. So that's the way I think of it. It's just pairs that we know have nice, convenient closed form formulas.
Exactly. Like you'll end up with a beta distribution here. If I'm not, yeah, you will end up with a beta distribution, essentially. So it does, and I'm just gonna skip ahead for a second. This exponential family that beta and Bernoulli and binomial and Gaussian belong to Gaussian, right? Yes, Gaussian. Basically like have this property that you can describe it with a finite number of values. Like for a Gaussian distribution, all you need to know is the mean and the standard deviation. For a beta distribution, all you need to know is alpha and beta. Makes it easy to compute. Like makes it easy to like say learn those values and then sample from that distribution. And so because they're part of the same family, you can actually, get a posterior distribution that is very easy to work with and, and easy to update. So the exponential family is actually the only, is defined by the family of distributions where there are a finite number of sufficient statistics, where sufficient statistics is like numbers that you can use to describe it fully, like mean and standard deviation. In the book, they talk about that vector of sufficient statistics being phi x, and these being the parameters. So you take the inner product of it, and then h of x and a of theta, those are like kind of just to make sure that it's like normalized. These can take like a couple of different, you know, values. They say in the book it kind of makes sense to ignore those sometimes just to get a more intuitive, you know, but just with the knowledge that they do sometimes take values, you know. So it's more or less like e to the power of these parameters times their sufficient statistics. So plugging it into say like a Gaussian distribution, we could take x and x squared as the sufficient statistics, you know, mean and standard deviation, and then we can multiply it by those two parameters, and then we can get this in its exponential form. That is like exponential family form, you know. And what we can use that for is this idea of like that proving that members of the exponential family each have a conjugate prior. Basically, like you can say like gamma 1 and gamma 2 are the like the new sufficient statistics, and you can multiply them by the old ones. You know, if we're assuming, I think they assume this is, yeah, they assume this is a Bernoulli distribution. And then they do like negative a of this parameter. So you actually need, like the beta distribution has two sufficient statistics. The Bernoulli distribution has one, and the what is it? Binomial distribution also has one. So you need the conjugate to have one more statistic than the original, because you have to multiply by this negative a of that, or the normalization parameter. So what this looks like in practice is basically you take this like exponential format of the Bernoulli distribution, and considering that gamma is the new parameters, which is, you know, and then h of mu, and I'm not entirely sure, I gotta be honest, I'm not entirely sure how they got this one, but I don't think, you know, unless I'm mistaken, this isn't the kind of thing that we really have to do by hand. I've never had to. But basically, if you substitute this in to this equation, you are left with the beta distribution. So you can turn the Bernoulli distribution into the beta distribution through this equation, which means that it's a conjugate. So, yeah. Any questions about exponential family or the conjugates?
I just wanted to make a comment about the parameterization that they show in the book here when they're talking about things being in the exponential family. Again, my probability in stats is weak, so I struggle with these. I think the best analogy I can give is like in high school, there were times in math class where we talked about you can talk about things with Cartesian coordinates or polar coordinates, and like a circle, like the unit circle is x squared plus y squared equals 1 in Cartesian coordinates, and in polar coordinates it's r equals 1. Okay, and they're the same circle. It's just a different parameterization of how you are talking about that object. And so it's sort of the same thing here, is that the Gaussian distribution is the same, but just like Cartesian versus polar, you have a different way of dividing up the information. But if you have the xy plane, it's always going to be two things, and polar coordinates, it's going to be r and theta, it's two things. And no matter how you do it, you're always going to have two things in order to describe things in a plane. It's sort of the same thing. If you have two sufficient statistics, whether you use mean, mu, and standard deviation, sigma, or you use a different parameterization, it's still going to be two numbers. It's just, you know, they get used slightly differently. So I have seen in some places where people are talking about Gaussians, but they're not using mean and covariance. And that kind of throws me for a little bit of a loop. I don't really have any intuition on the other parameterizations, but I do know that, like, okay, fine, I know it's still going to be two things, and it's going to boil down to the same thing, but just like, for example, in if you have a point and you want to add something to it in Cartesian coordinates, it's really easy, and it's a pain in the neck in polar coordinates to add two things together. But multiplying things is a little bit of work in Cartesian coordinates, but multiplying is really easy in polar coordinates. Okay, it's the same thing. Sometimes if they have a different parameterization, then that's just more convenient for them to do the operations that they want to do versus the mean and covariance parameterization.
I think I'd like to actually mention, Maya, you mentioned that beta distribution is used for policy search. I think that's kind of fascinating. And you mentioned something about AB pruning or alpha beta pruning. Are you able to maybe go into a little bit more detail as far as that goes? Oh, we are? Oh, okay. Sorry, never mind. We might actually be over time. Wait, I can't hear anyone. Oh, okay.
I don't know if people are talking or not. Sorry.
I think we might have to wrap it up actually. Yeah. Yeah, because that could be something. But that's definitely something I personally will be looking into in the future. Thanks for sharing that. Definitely appreciate it. But yeah.
Do you have any more slides? I think that's the end.
Yeah, there's a little more, but that's
Okay.
pretty much it. Yeah. So yeah. All right. Well, thanks everyone. I think that's
All right. Thanks, Lance.
Yeah.
All right. I'll stop the recording here.